Yeah, this is the menagerie. Yeah, the menagerie of possible worlds. So we're doing this now, right? We're finding other planets, and what I wanted to talk to you about today, just maybe for 40 minutes or something like that, maybe 35. We'll see what happens, and then we'll get to the assignment for next week because it's kind of an extensive assignment where you have to wade through the data. So I want to give you plenty of time. We're going to work on it in class a little bit today, and then on Tuesday. Okay. So searching for these things, and the question is, how are we looking for them? How are we finding them? And what are we finding? What do we expect to find? What haven't we found? And what bizarre things people are starting to find that we didn't expect. Just as a way of an introduction to this, to give you an idea of the things we're finding that we never thought we'd find. Hot Jupiters, we talked about those. Evaporating planets. They found planets that get bigger and smaller and bigger and smaller, and the only explanation they have for this, other than somebody communicating with clacks, is that it's like a giant, massive planet, like a comet, where the atmosphere is blowing off because it's so close to the central star. They have recently found some Earth-sized objects that are too massive for their size, and they think they may be the cores of evaporated planets that got crystallized at a very high density. So it's like an Earth size, but the entire planet is heavier than iron, denser than iron. And the only way that could happen, like if it happens slowly, the planet would relax, right? If you had a Neptune that suddenly lost all its mass, the core would just relax into something bigger. But if you could somehow get rid of all of the mass on the outside quickly through a giant impact or something like that, the core would cool so quickly it would crystallize in that heavier state, or that denser state. So these are just bizarre things we're finding, none of which are found in our solar system. So it's a testament to the act of observing, because when you go out to observe, you can try to predict what you're going to find, but you have to let yourself open to the fact that you're going to find things that you never predicted. Okay? All right, so I pulled this up a month ago. I didn't bother to update it. These numbers aren't exact, but we talked about this stuff. Not all of these are in our candidate catalogs, but there's 351 objects in the Kepler database, if you go to their website, that their candidates claiming are smaller than the size of the Earth. Okay, and 30 of them, depending on who you talk to, what their atmospheric conditions might be, there's all these debates, approximately 30 of them we would call them habitable, right? And what that really means is they're as close to Earth-like as we can get. That doesn't necessarily mean that non-Earth-like planets aren't habitable, right? It just means that there's something that's habitable. So this is where we are. We've gone from 1996, where we knew nothing, to today, where this is where we are. And you're basically going to double check this number for me based on your assumptions, based on our assumptions in your assignment. And we'll see if we can maybe make that number a little bit bigger. Because again, this is only Earth-sized planets that are close enough to the star to potentially have liquid water on the surface. It excludes moons, it excludes super-Earths, it excludes the possibility of transiting planets close to white dwarfs, which white dwarfs are dead stars, but they're still hot, and if you're close enough, right? So I wanted to talk a little bit about how we find these things, these planets that are out there, because we're not seeing the planet directly in almost all cases. A vast majority of them, we're seeing them indirectly. So these are the types of telescopes that people use. These are the Keck telescopes at Mauna Kea. Those two Keck telescopes, each one is 10 meters in diameter. I think this is an infrared observatory, and this is a sub-millimeter observatory over here. But those two optical telescopes, 10 meters is like half the size of this, or twice the size of this room. This is maybe 5 meters across, would you say, roughly? So imagine, right, twice the size of this room. This is a 5-meter radius, this is a 10-meter diameter. So you'd be sitting on half of the mirror. So these are big telescopes. And what's interesting about these is they're not looking at terribly dim stars. When we talked about telescopes, the bigger the telescope, the better your resolution, the more light you can get. But what we're trying to do with this is look at the spectrum of stars, very high resolution spectra. And in order to see that, you've got to see it, you've got to take in a lot of light to get that high resolution spectrum. And so a lot of the stars we're talking about are stars you can see with your naked eye. but we have to use these big telescopes to do this. From your basic physics, you remember center of mass. I found this, I was out, my research group on the beach in Washington. This is the center of mass. Somebody built this. I did not do this. I was just walking along the beach in Washington, the Puget Sound's over here, and I found this thing that somebody put together because they were bored on the beach. Because you can't go swimming in Washington, it's too cold. So, but center of mass, you all know the concept of center of mass. If I put more weight on one side, I have to move the center of mass over. If I put more weight on the other side, I have to move it back. And every single object that either orbits or interacts in any way rotates about the center of mass. Not about, we talked about Kepler, where you imagine a fixed planet or a fixed star planet going around these. All planets and stars do this. Now, a really small planet, the star doesn't move very much. Big planet moves a lot, right? So we can use this to gravitationally detect the motion of these systems, right? So the center of mass is right here in a two-body system. They'll always be right opposite each other. Those who took 2300 will recognize that awesome video there from our presentation there. So I can take two stars, and we've been doing binary star detection for a long time, but I can see both of the stars. Right, so I can, when I do a light curve or something, I can tell that I'm seeing the light from both stars. But for a planet, it's going to look more like this, and this little star is just going to wobble around. And what's a fun experiment you can do is you can add in a bunch of planets, and you'll find out that the wobble just becomes more complicated. So if you just have Jupiter and the Sun, the wobble looks like this, so the star is just going like this. If I add Jupiter and Saturn, now it's going to go like this. Right, so you get like a circle on a circle. And if I add Uranus and Neptune, it's going to be a circle on a circle on a circle on a circle. Right, and if I add in all the lower mass planets, you just get a complicated little spirograph thing. And you can back out, depending on the resolution of your data, if you measure the velocity of the star or the position of the star, you can map out the influence of all those planets. Which now we're getting to the point where we can detect 2, 3, 4, 5, 6, 7 planets in a system. So a couple ways we can do this. The first two ways are going to be using this motion. One is called astrometry. That's where you're looking at the motion of the star on the sky. Okay. The other one is Doppler effect, where you're looking at the motion of the star from its spectrum. So that's when you see it. We talked about Doppler shift. Yeah, so you get Doppler shifted red shift, Doppler shift blue shift in the lines. And then the third one still uses this motion, but it looks at the transit, the dimming of the light as the planet goes in front of the star. All of these methods are useful. The only one that hasn't been successful in detecting a star is astrometry. And this is just to give you an idea of why. So this is the motion of a star. This is Barnard's star, which has a stellar companion. And look at the dates on here from 2000 to 2001. I think we go to 2002. It's hardly moved at all. So we can detect the motion, but if this was a planet, right, we would need to, if it was a Jupiter planet, we would expect it to do a full circle. So clearly whatever's causing this to move is not a Jupiter mass planet. If it's a stellar companion, it would have a much longer period, maybe 1 million years. Right? So the problem with astrometry is that to see stuff, you're sensitive to far out things, and you're sensitive to anything that's creating a large motion, but it's going to take a really long time to observe. So if you wanted to observe Jupiter, you're talking a decade just to see it move through one orbit. So astrometry has not been successful. Doppler effect, on the other hand, has been successful. So this is, again, the shift in light frequency as the object is moving towards you. This is the easiest way to do it. And we can now measure the Doppler effect of stars that are moving with less than 1 meter per second. So 1 meter per second is, right? That's pretty tiny. That you can detect a 3 Earth mass planet around a red dwarf star that way. So this is pretty intense. And this is by far the most successful method. The only problem with this method is if you're edge on, it's perfect, right? Because it's always towards the way. If it's face to you, you don't see anything because it's only the motion or direction. So there's this ambiguity about the mass, because if I'm edge on, I get the actual mass, but if I'm like this, I'm actually measuring only the minimum mass, because if it was edge on, my mass would be seen as bigger because of the component of the velocity in the line of sight. And then transits are probably conceptually the easiest way to do it, but we just wait for a planet to transit across, and we see a dip in the light. And the cool thing about this is that you can you can measure the size, which is nice, but you can't measure the mass. This only gives you the size. Now, many of our objects, we have transits and radial velocity, and then you can do science because we've got density. We've got size and mass. But you can see this is a relatively small planet. The smaller the planet gets, the shallower this is. Depth has to do, what does the depth tell you? Or sorry, depth tells you the size. What does the duration of the transit tell you? It's orbital period. So you really get two things. You get size and orbital period, no mass. All of the Kepler candidates have size and orbital period, but no mass. So you can do some cool things. I mean, if you make some assumptions about the properties of matter and what the material planet is made out of, you can get masses, you can infer masses, but you don't know directly. And a transit of a white dwarf in front of a solar-type star would look the same as an Earth in front of a solar-type star, because the size of the white dwarf is the same, and the duration of the period would be the same. Well, that's not quite true, because you have a solar mass. The light intensity would be, the white dwarf is so much dimmer than the star that I don't think it would matter. So you do have a little bit of ambiguity there. This is Kepler, though. This is the mission so if you think about it, most of those other data points in the catalog that you're going to be looking at are from various researchers using different telescopes around the planet. This is the only instrument that Kepler used. This is the Kepler spacecraft. It orbited a distance from Earth. It stared at the same spot of the sky, which looked like this. This is the Cygnus constellation. If you go out in the summertime, look up and find the Cygnus the Swan, look off to the left between Lyra and Cygnus, or off to the right, you'll see the spot. They wanted to look near the plane of the galaxy to get as many stars as possible. They didn't want to look exactly in the plane because the galaxy obscures a lot of stuff with its dust. And then each one of these is a CCD camera. And the telescope's only about this big around, but the key was to get a big field of view. And as we talked about with telescopes, what do you do to get a big field of view? You pave your optical field in silicon, right? So it's basically like a giant solar cell with pixels on it. Now I got to see this instrument being developed, and the way they tested to see, so this instrument can see dimming of the star to 1 part in a million. And the way they tested it is they took an LED light and they put a monofilament wire across it. And then they put their camera on it, and then they would send a minuscule amount of current through the wire to make the wire slightly thicker or slightly thinner, because when you put the current through, it heats up and it gets a little bigger, a little smaller. And they did that so that the change in cross-sectional area of the wire was 1 part in a million, and then they made plots of that. So they tested it in the laboratory before it flew in space, and it was pretty impressive what they could do. They chose a field of view also that had 3 known transiting planets. These are like the test planets. If they couldn't find those, the instrument didn't work. Right? So this is the pre-Kepler planets in the field. After the first data release, it looked like this. Every single yellow dot there is a star with a planet of some kind. And I love that because, you know, in less than 6 months, right, they found, and pretty much that's almost all of them. Right. If we look at this broken down in size, now this is the full catalog that's been released, all 2,700. The blue ones are Earth size. The green ones are super Earth size. The orange ones are Neptune size, and the red ones are Jupiter or larger in size. Right. Gas giants. Now we're assuming these are rock, and we're assuming gas. We're assuming these are like Neptune. We have no idea what the state of these are. We have no benchmark for what a super Earth is. Could they be these evaporated cores that we talked about, where they're more massive than they should be and rocky, or are they something else entirely? So that's cool that we found that. I think that's pretty interesting.
I want a jello planet.
Maybe
that's what they are. I mean, maybe it's like rocky.
Yeah, exactly. Yeah. I mean, we don't know. We just know that they're more massive than they should be based on their size and what we know of. So there's two ideas of the super Earths. The super Earths are either Earths that are slightly bigger, but they're made out of rock, and they have water, and they're, whatever, just more real estate. The other thing is that they're, and I think this is more likely given what we have seen, but you'll get to decide this for yourself. When you take a Neptune and move it towards the sun, and then evaporate its atmosphere, and blast off all the volatiles, what you're left with is going to be about a little bit bigger than the Earth, but it's not going to be made out of the same stuff as the Earth. It's going to be a dense, because it was the core of a giant planet that got super compressed. So we have to confirm. Remember, we don't know their masses, so we can't really know that. We're starting to learn about their masses. Now, this is the most interesting thing, I think. You can ignore those increases in percentages. That was the increase from the first data release. But I find it fascinating that if you look at our solar system, right, our solar system has Earths, Neptunes, and Jupiters. And if you were to make a graph for us, it would be Mercury, Venus, Earth, Mars. So this would be 4. You would get 2 for Uranus and Neptune, and you would get 2 for Jupiter and Saturn, and you wouldn't get any here, and you wouldn't get any here. But if you look at all of the planets we've discovered, right, we see that now, we may not have found all the Earths yet, so ignore that one. That's a sample bias, probably. We probably haven't seen all of the Jupiters yet, because those could be on longer periods, right? But the fact that we're seeing almost comparable super-Earths and Neptunes means that our solar system should have 2 Neptunes and 2 super-Earths, or maybe 1 super-Earth and 2 Neptunes. But we don't have any. So statistically, there are as many super-Earths as Neptunes. There should be in the galaxy. And we don't have one of those. So it's not just like this oddball thing, yeah, we don't know what that is, but it doesn't really matter. It's going to be one of the dominant types of planets in the galaxy. So not understanding it means we don't understand. If it's potentially habitable, that's a lot of real estate. If it's not potentially habitable, that's even worse, because that's a very common. Now maybe the Earth size goes, and maybe it is 4 times or twice this really. But we do know that these are statistically significant. So that's a huge finding. These super-Earths, these things that we have no idea what they are. And they're only 1.5 to 2 times the radius of the Earth. But because of the mass scales like the radius cubed, if you're twice the mass, you're 8 times, or twice the radius, you're 8 times the mass, roughly. And so these are relatively massive things. Now you could go ahead and start doing some playing around with some modeling to figure out what the surface gravity is. But you'd have to make an assumption of what the mass is versus the radius. And we don't know what the mass is. We're just saying if it's the same density as the Earth, which we don't know that. In fact, I bet you it isn't. Okay, so this is just a little schematic of how we then factor these things out to get at what's habitable. Most of these, remember, Kepler's only been going for 4 years, which means really only 3, right? 3 observing years. So we're just barely getting out to being able to tell what's in the habitable zone for sun-like stars. So this would be the Earth, 1-year orbit. So you might see 3 transits in the Kepler lifespan. The hotter stars, we're not going to see habitable planets because we didn't have enough time. But the cooler stars, and this is where the real research is coming out, the cooler stars we are finding lots of planets. That's where we're seeing the ones in the habitable zone. And that's exciting because not only they're in the habitable zone, because they're low mass stars, there's some chance that we could confirm them with radial velocity techniques, get masses. So the big area of research is focusing on super-Earths in the habitable zone of low mass stars, because we'll be able to confirm them, and we'll have radii and masses, we'll have densities, we'll have orbital properties, and it's a whole new class of object. So I think that's, if you're looking for a research project, right? No, I'm serious. Like there's like 8 people doing this. There's tons of data, right? And the data is freely accessible. Just download it off the web. You don't need to know anybody. Okay, so expectations. So that's what we found. What are we expecting to find? I've got 2 pictures here. Does anybody recognize these worlds? This is the forest moon of Endor from Return of the Jedi. You have seen Return of the Jedi. Okay, thank you. This is Pandora. Yeah, I told you I wanted to start off my astronomy class that way? Remember where he walks out and he's like, my job is to get you to pass this class. I will not succeed. No, that's... Anyway, Pandora. Pandora is a moon of a giant planet around Alpha Centauri. Okay, Alpha Centauri A, I think. I have to go look up it on Wikipedia. It's a moon. It's a habitable moon, right? The reason I'm showing you this is because the next thing they're trying to do with these transit observations is to see if there are any moons around these planets. And the cool thing about that is that you can, if there's a center of mass between the planet and the star that causes the star to move, and you have a planet transiting, right? That's going to have some timing. If you've got two objects, that's going to happen every so often. But now you have a massive planet and a moon that's doing this around a center of mass, which means when it comes around for the transit, if this is the star, right, sometimes the moon is leading, which means the transit will be delayed because you can't see the transit from the moon, just from the planet. Or sometimes the moon will be trailing and the transit will lead a little bit. And so it's called transit timing variations. And this is the thing that is requiring armies of students to look at, right? Because finding a transit and then folding it all together and being the big mucky muck professor that publishes the planet finding is easy, right? Monitoring the timing of every single transit. If you've got a planet in the habitable zone of an M dwarf with a 12-day period, you get a transit every 12 days for 3 years, you have to analyze the timing transit, which means you have to fit every transit with a curve, find the minimum, find the exact time the transit occurred, map out the transit timing. That is something that takes an awful lot of work, so that's why we haven't seen it yet. And it's not something that's easy for computers to just dump out, right? It's also entirely possible that we're missing some transits because you've got two planets, binary planets, going like this, which the transit is so varied that it's not even being picked up in the algorithms to look for transits because it's not repeatable enough. Because how do they find these transits? You've got 100,000 stars. You're taking data every 8 minutes, I think it is, if I'm mistaken. I have to look that up. Anyway, you're frequently taking data on 100,000 stars. You can't look at that, right? You have to have a computer find the transits for you. If your transits are varying by a certain amount, it won't even notice it's transit. It'll say, oh, that didn't happen at intervals. Right? So they're going back to the data. In fact, one of the Weber State graduates, Jason Stefan, is working on this very project. So it's a cool idea by looking at these transits. It's an awful lot of work, which is why we haven't seen it yet. But I suspect, given that we have binary planets in this system, Moon, Earth, we're going to start finding binary planets, or at least Jupiter masses with moons.
Yeah. That's my question, because our moon is so big. How far does that throw off? How
a lot. Yeah, so you can calculate out, well, in terms of the transit timing, it's significant. I mean, well, okay, here you can do it pretty easily. Roughly the center of mass of the Earth-Moon system is about an Earth radius, let's say, right? I think it's slightly smaller, but so what's the light travel time for the Earth, the size of the Earth? Because that's really what you're saying is what's the transit time? Yeah, I don't think you're going to be able to find the moon because 6,000 kilometers or 6,000 kilometers, and it's 300,000 kilometers per second. So.
A few light seconds away anyway.
Right. So. Yeah. So it would change the timing by fractions of a second. However, if you're observing that over 3 years and you have a transit around a red dwarf every 6 days. Right? You just have to beat down the noise, right? That's the key. And if you've got timing of 800,000 transits, or whatever that turns out to be, 3 years divided by, well, it's not 800,000, but 3 years divided by 8 days, that's a lot of transits. So you may not be able to do Earth, Moon, but you can certainly do Jupiter and Callisto, or Jupiter and the Earth. Because I'm just going to throw this out there. I suspect that if we live in a planet, or if we live in a solar system that doesn't have super-Earths, we probably live in a solar system that doesn't have binary super-Earths. Or Neptune with an Earth-size moon, or something like there's probably all sorts of weird situations. So the key one that I've got an a Weber State alumni at the U for his PhD dissertation is looking at a Neptune with an Earth around a a low-mass star as the first possible observable case. And he's looking at it for stability and some dynamical simulations, but it's something that he's working on. So that's one expectation. The other expectation, wait, I missed, where's my, no, I missed my, I thought I had the totally cool slide in there. Oh, dang. Well, I guess I'll just have to tell you about it. Tatooine. I guess it's not in expectations. We've already found it. Tatooine, we found stars around or planets around binary stars. Now this is exciting because it was thought for a long time that binary systems were too unstable to have stable planet formation. And even when Star Wars was first written, George Lucas went to the scientists and said, "I want to put two suns around this. Is that plausible?" And they're like, "No, that's not plausible." And he did it anyway because he wanted to evoke an alien world, and the best way to do that is put two suns. You know, we got Luke Skywalker looking out over the horizon, two suns. You know it's not on Earth. Well, they found one. Now it's a Jupiter mass planet orbiting two suns, but if there's a Jupiter mass, there's probably an Earth mass in there someplace. The other thing they found is a planet orbiting Alpha Centauri b with a 3-day period. Right? And people had said that Alpha Centauri, which is a binary star system, was too dynamically unstable to form planets. Well, they were wrong. And we found one. Now, it only has a 3-day period, but that probably means there's others. And we did a little simulation in class to show that it's relatively stable out to the habitable zone. So, all right, so now that's what we've learned, and that's what you're going to work on for your assignment. All of that data, we're going to wade through all that, and you can answer some questions that we have not talked about. And there's some little kernels of research projects that have yet to be completed in there if you get interested in this type of stuff. But what's the next step? And I think this is exciting because the next step is to view the planet itself. We haven't done this yet. We've done it with a few large planets at very far separations, but not very interesting things from a astrobiology perspective. So the next generation is to basically build a free-flying occulting telescope, because we have the telescopes to see the planet if the star wasn't there. If it's just the star is so bright we can't see the planet next to the star. So we need to block out the starlight from the planet. And the only way to do that is to put your thumb up in front of the star, right? But the problem is you can't get your thumb far enough away from the telescope to do it. So they're talking about flying this funky shape, and it's this shape because it reduces the diffraction around the occulting disk. But is basically, the concept is fly a giant thumb in space with a free-flying telescope to block the light. Now the only trick about this is that to do this thing has to be huge, and the separation between them has to be enormous. So we're talking about well, this doesn't really give it to the scale, but we're talking about something that's several kilometers across, tens of kilometers across, and a space telescope-sized telescope that's orbiting hundreds of thousands of kilometers away. So this will be new, right? We're talking about coordinating satellites. Now, it's not totally new. We do this with satellites all the time. We wait for we've done this to study binary star systems. If you wait for a planet to occult a star, you can block out the light of that star and see its companion, but it's just a chance, right? So we're basically taking the chance out of it. And what you do, the cool thing about this is you would line these things up, you know, slew them through space, line them up, take 40 days of observations, and then you're done with that star, and then this telescope can go do other cool astrophysics while this thing flies or orbits halfway around the solar system to get someplace where we can look at the next target. So it's kind of a nice hybrid mission. We'll get a lot of cool science out of it that has nothing to do with astrobiology, but then every few years we'll get an observation of another planet. And the idea is that you would be able to resolve pixels on the planet itself. And once you've done that, then it's just a matter of collecting that light and analyzing it, right, and trying to figure out what's going on. Now this is a step that I think will probably happen in the next decade or so. I'll ignore the fact that I've been saying that since 2000. Hasn't happened yet. But still, if we can do this, I think in our lifetimes, hopefully mine, certainly yours, you will be able to see a graph of the atmospheric constituents of that planet. And so you'll be able to look at this planet and say, yes, there's oxygen, yes, there's nitrogen, yes, there's carbon dioxide. That is a good target for a planet with life, or a potential planet with life. But that's a whole nother talk. Anyway, so to finish up here, I like to put this up. Oh, I thought I changed that. Anyway, it's supposed to say 2013 down there. This is when I started in my undergraduate career. And in my astrophysics class, we didn't talk about exoplanets at all. They weren't even mentioned. They didn't even, in fact, we barely talked about the planets. He thought planets were boring. He was an extragalactic astronomer. But zero. There were zero in 1994. In 1998, there were 30 giant planets, super hot Jupiters, and this is what we have today. Now, where you're sitting, though, in 2008, there were zero. That's when Kepler launched. Or sorry, there was zero in 2008. Then in 2012, Kepler launched. There's 351 so far. The number with life, I predict by 2020 we will start getting the first data that will allow us to answer that question. Because if you find a planet that has oxygen, carbon dioxide, ozone, and nitrogen, all of those are dominated by life. If we didn't have those, we'd have a CO2 atmosphere and nothing else. So I predict, and you can see if this is true, 2020, I think we're going to find this. And I think we're going to have this answer. And in fact, I went and visited one of these planets. See that? This is Meteor Crater. But that's not even the coolest thing. I forgot to show you the coolest thing. We were talking about life on other planets. The thing that makes me most excited about this possibility. Whoops, that's not going to work. Hang on. Oh, don't look at my password. It's star, 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 star. That's right, circle, circle.
They were low resolution stars.
Yeah. If we find another planet with life, you may be able to find some more baby goats. We had a baby goat this morning. Look at that little baby goat. She was born last night. Isn't she sweet? Yeah. Little baby goat. See, this is exciting to me because I would love to find another planet with life, because if baby goats are this cute, I can't even imagine. Yeah. The nice thing about baby goats is they come out with fur on them, so they're not as slimy as other kids, human kids. They're cute, right? They're adorable.
They walk around a lot quicker.
Yeah, they do walk around a lot quicker. So anyway, so all right, so
Well,
now.
because we give birth before we're actually ready.
Yes, that's the other thing too. Now, okay, so that's sort of a summary. Now what we're going to do here for today and the next time, if we log in, go ahead and fire up your Canvas. I've put your assignment 8, and we're going to work on this in class a little bit, not entirely, but a little bit. And it is on our Canvas site. Any questions about these things before we move on? You will have questions as you go through your assignment, I'm sure. But. Okay, so this is assignment 8. And I apologize, there must have been an update to Canvas. This is something I find kind of annoying, that all of a sudden the assignment doesn't print.
Yeah.
It's this weird sort of box thing. So I apologize for that. If you'd like, I can put this in a sheet of paper PDF that you can download if you prefer. Or you can just put it in a different window or something like that. But what you're going to be doing is using the exoplanets.org catalog. And you should be able to do everything on this assignment using the tools on the website. If you don't want to use the tools on the website, you can export all of the data to your favorite spreadsheet program or C++ or whatever the heck you want, and do whatever you like. But I want you to go through the database, and I've tried to kind of guide you with some questions to answer, but I'd like you to read through all the questions before you go to see what you're doing here. So one of the first things you're going to do is look at something called observational biases, because every single time you observe anything, you have an observational bias dictated by the instrument or the technique you use. And so this will help you explore some of the observational biases for the two techniques we've been talking about, transit and radial velocity. The next thing you're going to do is look at what planets we're most sensitive to, right? And try to see what that distribution is. I want you to make a few histograms of planetary properties, and you can walk through that. I also want you to see if you can determine what's called the mass function. So we've observed enough planets now that you should be able to fit a function to the number of planets of a certain mass. and see, extrapolate that to lower masses and to higher masses. So we're going to play a little game, and I don't know if n to the minus alpha is going to work too well anymore because we're getting this kind of bimodal thing, but maybe we'll just use, I guess if we're doing masses, we'll just use the confirmed planets. If we use Kepler, we get that weird bimodal thing. So if we just use the confirmed catalog, we should be able to fit a mass function. Will let you extrapolate how many Earths there should be, right? Excuse me. And then I've got you exploring some correlations, but the final big part of this is looking for habitable worlds. And so your job is to figure out how many habitable planets are in each catalog and how many possible habitable moons could be in this catalog if you assume that there are moons around some of these stars. So this is that's the goal of this thing, is to get through that. It's going to take a little bit of just plain old inquiry and exploration. You just have to play around with the tools, see what you can find out. But hopefully this will guide some of your instruction. Now I think almost everything in this you should be able to get done. You know, these first parts I think you could probably do today, probably up through, well, certainly by the end of class next time you should be able to get up through number 5. 6, 7, and 8 are going to be a little bit more involved. So, but we can at least get started. Any questions?
Maybe later.
Maybe later. All right. We'll go ahead and get started.